Good morning, or good afternoon, or even good evening. My name is Eugenio Oñate. I am a professor in structural mechanics at the School of Civil Engineering in the Technical University of Catalonia in Barcelona, UPC, and also the director of CIMNE, the International Center for Numerical Methods in Engineering, a center that was created some 25 years ago and now groups some 220 researchers from many different countries. One of our most active lines of research is the development of new computational methods that merge techniques coming from old methods like the finite element method with new approaches, some of particle-based methods. In the next minutes I'm going to share with you our recent results and developments in the so-called particle finite element technique. You will see that this marriage of technologies opens a wide number of possibilities for solving problems that were almost, I think, impossible to be solved in the past. Problems where water and structures interact, where fire and solids melt and are interacting, interchanging information. Anyhow, I hope you will enjoy this presentation and that through this new video conference tool we can share many moments in the future. Thank you. So it is my pleasure to introduce you to the recent developments in this new technology called the particle finite element method, PFEM for short, and the many possibilities of this approach for solving a wide range of problems in engineering. This is a collective effort, and in the slides you can see the number of people involved. Senior scientists like Professor Erosion in CIMNE, Professor Suarez in the Technical University of Catalonia, postdocs like Dr. Rossi, Dr. Demir, Dr. Rizkahov, Dr. Carbonell, from different countries, from Italy, from Argentina, from Russia, and junior PhD students, Miguel Ángel Feligueta, Antonia Larese, and Salvador Latorre. Just to name a few of the large number of people that now are involved in developing this method and reflecting also the many possibilities for solving complex problems in engineering. The research is carried out in Barcelona. You can see that this is a city well known all over the world in the northeast coast of Spain. And you can see snapshots of the harbor area where the Columbus statue is pointing towards the sea, and the many nice boulevards like Ramblas ending up in the harbor, the Gaudi church, the cathedral, and other really landmarks in the city. I'm going to go briefly through the basis of this approach and some particular features of the method, how to treat frictional contact conditions between multi-bodies in water, how to model wear and erosion due to water forces, but also due to frictional contact situations, and mainly focus in the applications in different problems. You can see the list here, from ship hydrodynamics to industrial foaming processes. Now, the motivation of this development started when we were faced with the solution of a problem like this one. This is a wave which is going to hit the shore, and you can see that these large displacements in the water surface, the separation of particles, splashing. In summary, a very difficult problem to solve with classical methods in computational mechanics. And this is a problem of very important relevance. In fiction magazines like this one, we can see the night dream or nightmare of designer imagining that a big wave was going to hit Scotland, Edinburgh, in England, in Great Britain. But this is not only the dream. This has been taken also to fiction movies like this one, where you can see that this big wave is going to hit the coastline. But of course, reality sometimes improves fiction. Unfortunately, in this case, for the worst. And you can see here some snapshots of tsunami waves impacting the shore. This was some of the pictures taken during the Indonesia tsunami. And these are quite dramatic pictures, but I don't want to sound too dramatic. I would like to emphasize how these people are fascinated by the waves. You can see here a gentleman taking pictures, and a few seconds later they have to run, and eventually you can see that they're going to be surrounded by water. And this is a gentle a picture, but in fact it could have devastating effects in people, infrastructure, and vehicles, etc. Of course, this is a natural problem. If you're dealing with in the naval industry, ships face the impact of large waves, like in this case, and we have to model this problem. And you can see here some snapshots of the method that I'm going to present you in a minute. These look like particles that are moving around. In fact, they are not particles, they are nodes in the finite element mesh, but you will see this in a minute. Similar problem in a different context, large waves which impact these concrete blocks, weighing sometimes 150 tons or more, and they are put as breakwaters in harbors. And in countries like Spain, with a long coastline, heavily exposed to the weather, like in the north of Spain, we have situations where the coastline is severely damaged by waves, and we have to model this effect, not only including how the wave will approach the shore, like in this case, but in many others, how also the wave will hit the rocks. And this is a 2D example, but of course, in practice, 2D cases are only benchmark problems, and we have to model the full three-dimensional effect, as in this example shown in the picture. Sometimes it's not the breakwater. The concern is the safety of people or infrastructure. A car which is passing and is hit by a wave. You can see here that this method has to account for the contact between water and objects which are moving, and between objects and walls. Another example, this is a wave which is actually hitting a lorry which is passing a side road. Now, it is common in areas like in the Mediterranean, where we have big floodings and the bridge foundations are eroded, and eventually this might induce failure of the structure. Some examples are shown in this picture. We have to model also this effect. And this also includes the problem of overtopping in earth dams, where water passes over the dam, induces collapse, transport, erosion, eventually failure of the structure. This was the case in the Tous Dam in Valencia in 1982. The whole dam was wiped out, and big damage occurred. Underground constructions under flooding or other effects, like for instance fire, which is another important problem that can be modeled with this technology. So a very wide range of problems, multidisciplinary problem across disciplines. So how do we approach the solution? We are going to use this technique called particle finite element method, because we're going to combine technologies from particle methods and the finite element method. And another keyword here is the Lagrangian formulation. Lagrangian versus more classical Eulerian or arbitrary Eulerian method, which are typical in fluid mechanics. not so much the Lagrangian approach that we're going to use. And it is going to allow us to model problems like this one. So how do we treat this problem in which we can see a body which is moving around and particles seem to be being expelled out of the flow? Well, let's start by considering how do we model a continuum with the particle method. In fact, in particle method, all the information is attached to a particle. That means each particle has information about velocities, accelerations, displacements, material properties that are transported with the particle. The particle carries the information in the motion. So think, for instance, that we have a collection of particles, and this is what we are going to use as a model for the underlying continuum. How do we compute the forces between particles? We could use, for instance, the so-called discrete element approach, in which each particle has a connection with the neighboring particles in terms of distance. This is typical in granular material or also in atomistic models, where the distance governs the forces between the particles. Sometimes it's the physical contact, sometimes it's an atomic distance. And these forces govern the dynamic equation of motion. Sum of forces equal mass times accelerations, or the same applies to the moments and the rotations, the angular rotations. This is the traditional method for discrete techniques. Now, we can use a different approach. We can use the particles as the basic information to build up a continuum problem. That means we are going to solve the equations of continuum mechanics in a domain that is going to build on the basis of the particles. And we are going to solve that problem, that continuous problem, using the finite element method. That's what we call this method particle finite element method. For that we need a domain, of course, including the boundary, and the mesh. This picture shows the essence of the method. Consider you have a collection of particles. Some particles are marked as solid, belonging to a solid continuum. Some others are marked as fluid particles. Some others are marked with a cross. That means they are fixed. Some are detached from the main domain, and some others are even floating in the air. Well, they are all used to build up a domain, and we go from cloud C to volume or domain at time n. This is what it means, n. So here we have now the domain that might represent, for instance, the water domain, and within the water we have an object which is marked in yellow. And we have some drops which form some external domain which we call flying subdomains. Now, because we have all the information from the particles, including the fixed particles, we can solve the problem in this domain, and we're going to use the finite element method. For that, we need to build a mesh. So we go from volume at time n to a mesh at time n. So here we press a button and we obtain a mesh here. And we are going to solve in this mesh the problem in which we are going to find all the state variables, velocities, accelerations, displacements, position of points, stresses, whatever we need to find at the next time step. And what is new here is that we are going to drop the mesh, we are going to erase the mesh, once we have moved the points, and we were going to have a cloud, the same as we had before, but not at time n, at 10n plus 1. Now this cloud at time n plus 1, shown here, is used as the starting point for the next time step. So we go from the cloud to the domain, from the domain to the mesh, from the mesh to the cloud. And you can see that those nodes that were floating in the previous transparence, now they have come closer and they have been trapped by the geometrical construction of the boundary. In this way we can detach and reattach particles to the domain. Another example, this shows what it could be a body under some contact forces, for instance, cutting forces, and we're going to erode, like in an excavation problem, erode the body, and some of the mass is going to be transferred to the underlying pan. Or this could also be an object, a polymer, that is going to be heated. Q could be the heat source that is going to burn the object. So in the first line we have the particles, the domain and the mesh at the initial time, and then at a certain time, and you can see that some of the particles are moving down, falling from the top to the bottom, and they are grouped sometimes in mesh domains, and sometimes they move as individual particles with its own mass. And this the process follows, and then we can have all the mass transferred from the top domain to the bottom in this sequential manner. So I think now we have understood how the method works. Some details, for instance, how do we reconstruct the boundary? We use what is called alpha shape method. Basically this uses the information from the Delaunay triangulation to identify the boundaries. Let us now see some details of the method. For instance, how do we reconstruct a boundary? For that we use information of the empty circles or the empty spheres in the Delaunay mesh generation. Basically this means that we pick up a circle of a certain diameter in 2D, and then we take 2 points, then we insert the 2 points in the circle, and if there is not a third point inside the circle, this proves that these 2 points belong to the boundary. And in the picture we can see the circles that identify the boundary points, and of course sometimes internal boundaries, so the reconstruction of the boundary depends on the number of points. These internal boundaries could be real or non-real. So the quality depends on the number of points, and here you can see that this point has been detached, or 2 points have been detached, and some of them form a domain, what we call a flying domain, and some points fly alone, and these points, if they are water points, for instance, when they come closer to the boundary, they are captured again by the geometrical algorithm. In that way, the mass that is lost can be recovered. If it is an excavation problem, this allow us to model the wear, the loss, the mass loss due to, for instance, to the cutting tools. And now we can understand what we are seeing here. In this picture, we see and we understand now how these points are moving and falling down, and they are trapped by the alpha shape algorithm. And of course, the boundary knows a mark with a different color. In fact, these points, they are not physical particles. They are plotted as spheres just for visualization purposes. In fact, they are nodes in the finite element mesh. For instance, if you see this picture, you might think this is a nice result, and what you don't perhaps figure out, that the secret is that what we are solving is this problem, as it is shown here. There is a mesh that moves around, and it is regenerated at each time step, as explained before. Another case, for instance, these 2 objects falling in the water, and the method behind showing that the mesh is being generated, some details of the mesh are shown in this picture. So always the secret is reconstruction of the domain, regeneration of the mesh at each time step in a very fast manner. How about the equations? The equations that we solve are those of solid mechanics or fluid mechanics in a Lagrangian framework. For instance, in this picture, we have a domain that could be a water domain containing a solid domain, and they both move in time from an initial configuration to a current configuration at time t. In time t, we know everything, and the challenge is to find out the state variables at time t plus delta t. So we're going to iterate from time t to time t plus delta t, both in the fluid and in the solid, until we find convergence and we obtain the final position of all the objects, one or many, in the solid and in the fluid domain. So basically this is what is called the updated Lagrangian formulation applied to the fluid or the solid domain. For instance, at time t we could have that the solid is floating, and at time t plus delta t the solid is submerged, and also its shape has changed, as shown here. The challenge is to converge from time t to time t plus delta t, because the equations, after all, if we are familiar with solid and fluid mechanics, they are not, in fact, they are quite simple. We have the equilibrium, or so-called momentum, conservation of momentum equation, which is shown here, and this is nothing else than Newton's law, sum of forces equal time, mass time acceleration, v is the velocities, rho is the density, sigma are the Cauchy stresses, f are the forces, external forces plus the boundary conditions, and we're going to split the Cauchy stresses in deviatoric and pressure, and we're going to have a constitutive equation governing the relationship between deviatoric stresses and rate of deformation, d, in terms of the viscosity, and the pressure and the relationship between pressure and the rate of volumetric strain. So here mu is the viscosity, and for a solid we have to add the previous stresses to the current, to this rate equation. So this is what we would call a memory material, a solid. In a fluid, this term is 0, so only the deviatoric stresses are a function of the rate of deformation. In the volumetric part, we have that the pressure is proportional to the rate of volumetric strain. A K is the compressibility modulus, which is infinity for the incompressible case, and the only equation that we have is dV equals 0. Now we could have the thermal balance equation written in this form. Q is the conductive heat, phi is the temperature, and you can see that in these two equations, in the momentum and thermal balance, the time derivatives do not include the convective terms because of the Lagrangian description of the motion. We could have boundary conditions in the standard manner, velocities prescribed on the boundary, and also the tractions are prescribed on the boundary, and these are written in the standard manner. So for instance, you can see here that in a free surface we will have 0 tractions, and in a fixed wall we have the velocities at 0. We then write these equations in the so-called variational form. We use weighted residuals, the Galerkin approach, where the shape functions are weighting functions, and this is the momentum equation, and this is the boundary condition for the tractions. And for the incompressibility, we write the volumetric strain equals 0 in this form multiplied by a test function, and we add this term here that is written for consistency purposes because we cannot solve the problem. We would like to solve the problem with equal order interpolation for velocities and pressure, and we cannot do that if we only use this term. So this is what is called the stabilization term, which is consistent in the sense that it will vanish for the exact solution. And this is the technicality that I will not elaborate any further. For the thermal equation, we have the equation, the boundary conditions, and we simply write the weighted residual form, the Galerkin manner, this equation times the shape functions plus the boundary conditions, integrated by parts. We have this equation that after discretization will give us a discrete system of equations. So at the end of the day, we have a problem which involves velocities, pressures, and temperatures, and any other auxiliary variables that we will have interpolated with the same approximation. That means, in our case, we use the simplest approximation, linear triangles or linear tetrahedra for 2 and 3D applications. Let us just recall, I will not elaborate much further, that we want to find out the equilibrium configuration in the fluid and the solid domain starting from a previous known configuration. We're going to iterate from here to here. And this we can do in two manners. We could use a program, a computer code from solid mechanics, and we apply to this, to the solid part, the forces coming from the fluid, and to the fluid part we use a fluid dynamic code, and we apply the motion, the velocities at the interface, and we solve two problems, one in the solid and another in the fluid, and we iterate, interchanging information, transferring forces, transferring motions, and we solve in this manner the solid and the fluid problems in the so-called stagger scheme. This is what is shown here. At each time step, S denotes the variables in the solid, F denotes the variables in the fluid, and for each one of these alternate or so-called stagger iterations, we solve for the solid problem, and this might be an iterative problem, and we solve for the fluid problem, and this might be also an iterative problem, and then we have the global iteration until we converge both for the fluid and the solid. A much modern and ambitious approach that we use is to solve for the fluid and the solid at the same time. That means that we take the solid domain and the fluid domain as if it was a single domain, like in a composite, and we solve for both at the same time the fluid and the solid variables. So for each time step we iterate and solve for S and for N, and until we converge. This we have done, the two methods we apply. If you are starting from zero, you want to rewrite your code, you might use this more, I would say, innovative approach. If you are using existing codes, you may want to use the staggered approach. For instance, in this case, we use the single code. This denotes like a block of ice which is floating and moving, and this was solved with a single code. Okay? So the program does not basically distinguish between a fluid and a solid other than from the constitutive equation. This is another case. We have a block of a column of water falling in a domain where we have sand, and you can see the sand is transported and from one side to the other. This is a very complex problem, again was solved with a single code. In most of the examples I'm going to show after this, we use the stagger approach. That means we iterate from the solid to the fluid using two different solvers. Now, a question that many people ask themselves is if mesh generation is expensive, because we need to generate the mesh at each time step. Well, in this picture we see the cost in time of solving the problem for each time step, split into the cost of solving the equations in yellow, the cost of solving for the meshing, which is called here in dark blue, and the rest of the computations. So you see that when the number of particles is small, around 100,000, the meshing time dominates the solution. But as soon as we go beyond 200, 300,000 particles, meshing time is not the most expensive part, is the solver, is the solution of the system of equations. In fact, we can see here, this is the cost of meshing versus the total time per time step, and we can see that this converges to something like 15-20%. So meshing basically is around 15% more expensive than non-meshing, so this is quite affordable. How about treatment of contact? Contact between solids, contact between water and walls. How do we treat this? Base is treated using information from the mesh. At each time step we need to mesh. So if we mesh, we will know how close are the bodies which are going to interchange information or interacting, from how close are one to each other, or how close are to the walls. So frictional contact is treated at mesh generation level. This means, for instance, that when we have water wall contact, for instance, in this moment in time, we can see that we have a jet approaching the wall, and in this particular time, we know that 2 points are on the wall and 1 point is in the interior, so we know that the mark element is interacting with the wall, and because of incompressibility, the point I can only move horizontally and will not penetrate the wall. So contact is detected at mesh generation level. So there is not a need for a contact search algorithm. See, for instance, this problem where we have a jet which is impacting a wall. And look at it with a bit more detail. For instance, this is when an instant before the jet interacts with the vertical wall, and you will see on the right hand side a particle which is detaching from the main stream and is moving faster until it gets close to the wall. In this moment in time, is being trapped by the boundary identification algorithm, by the boundary reconstruction algorithm, and at this moment, because of incompressibility, this particle can only move vertically, so it moves vertically, and in this way we constrain particles not to move out of the domain. This is a very powerful technique, as you can see here. But what is more interesting, that we can use the same philosophy to model the interaction between objects in water. For instance, see this solid which is approaching the boundary, and as it comes close to the boundary, we identify, because of the mesh generation, that elements have 2 points in the wall and 1 point in the solid. And we create what is called a boundary band, a contact band at the boundary, within each of these elements, we apply some constitutive law. Okay, so we apply constitutive equations for the frictional and normal forces, like in a contact algorithm, and this is done at the constitutive level for these elements in the boundary, and the effect is of a frictional contact layer. And you can see here in this movie, this object, which is bouncing, and the contact elements are marked. You can claim that the contact layer is very thick. Well, you can refine it, you can make it as thin as you want, increasing the accuracy, if needed, of the frictional contact problem. A number of tetrapods used to build breakwaters in harbor, which are falling, and this is a complex problem. They are interacting between themselves and with the walls, and you can see here that they can also, be thrown into water, and this complex problem of interaction between the objects and the water, and water with the walls, is automatically taken into account. From now on, I will focus on some experimental validations of the method and some applications. We have performed extensive testing of the method. Examples have been run together with some of our partners, like in the School of Naval Architecture in Madrid, within the framework of a number of projects. And you can see this is a tank which is oscillating, and we model very nicely the motion. But what is more interesting is that we can reproduce the pressure pulse quite accurately, both in frequency and height. This is not so easy. In this particular case, the tank is moving at a frequency close to the water frequency, and we have the phenomenon of beating. This is shown by the water getting still while the tank is still moving. So the water stops moving, and this is reflected in the pressure drop despite the fact that the water, the tank is still oscillating. Objects, flexible bodies in water, and we follow the displacement of the elastic band as it is hit by the water. In this case, the band is submerged. Or this case, which is a problem solved in our lab, hydraulics lab, where we have a tank, we have a vertical wall, a gate, we open the gate, water will flow, and we measure the height, the water height at different points. And this is a typical example that is run by our students. And in fact, some students do the experiments, some others run the code, and this is the students running the code. And you can see here what he obtained. And which is quite extraordinary is the comparison with experiments is relatively, well, I would say more than that, is quite good. So again, these are comparisons of heights of certain points in time. How about applications, for instance, to the natural problem, which is the impact of waters, of waves on ships? Well, we have performed extensive applications in this case, and this is one of the many what we call ship sinking simulations. So we model different scenarios of sinking situation for a ship. These are oil tankers, most of them. We have several accidents in the Mediterranean, also in Spain, and this has been a major effort in trying to model these type of problems. So this can be used for this purpose, but of course this is only a 2D problem. It gives you plenty of information of water motion, pressures on the walls, etc. But now we are applying the method for more, I would say, complex problems in 3D. This is a simple academic problem. This is an egg with a little hole when this is sinking, and you can see here that at least the physics of the problem is nicely reproduced. And now we are applying these to different problems like this one, sinking different objects. And recently, a problem of interest is how ships will interact with ice. This is a picture of ice hitting a boat. So this is another application, ice mechanics, of interest to the naval industry, in particular for the opening of the pole routes. Changing of topic, how about a sea landing of a satellite capsule? In this case, we model both the landing, I mean when the capsule hits the water, and also later on how the capsule will float in waves. So two floaters are added, and the particle and the capsule has to sustain the wave loads during a certain period of time. Well, other problem, this is a cloth used for cleaning in the harbor, and you can see the cloth is moving, and particles are being trapped. But these oil particles have been adhered to the cloth. This is just an example of how membranes and fluids can be combined in this technology. In fact, this is not a membrane, but this is a thin shell. This is a thin aluminum shell containing air that is put underwater, and the pressure of water will induce implosion. That means the shell will collapse, and this collapse is going to induce a pressure wave that can be of relevance and could induce damage in adjacent structures. So this is a 2D replication of the problem. You can see here that in this picture we show how the cylinder diameter is reduced until collapse is produced and the implosion is generated. And this is another example. You can see the air domain is reduced, and then you can see the pressure wave. And this is how the pressure, this is how as the diameter is reduced, and then you can see this big pressure wave, which is like letting water fall from a high distance even though a very short distance, but a big column, a high column of water falling and inducing this force, which, as the fluid is incompressible, will propagate in water. There's another case. In blue, we see the air, and the air is being reduced again and again and again until it's collapsed. In this case, it was a glass cylinder, not an aluminium cylinder. This was a glass cylinder. The aluminium cylinder case is shown in the next transparency. You can see there is a rebounding due to the small compressibility of the water. But in this case, this is an aluminium cylinder. And here we have to model the shell. That means the surface of the cylinder using shell elements. We have to model the contact between the shell walls when we have self-contact. And we can have to model for the discontinuity between the pressure in the water and in the air. So we have, in fact, three domains: the water domain, the shell domain, and the air domain. We use a continuum velocity approach and discontinuous pressure. This is a technique that we have developed. And here we can see some results. For instance, in this case, how the cylinder changes the shape until absolutely collapses due to this pressure. This is the increase of pressure, and let's see if we can see in this picture, for instance, in the upper part, how you see pressure starts to act and the walls are going to collapse. This is a cut in the cylinder, you see, and complete collapse is induced. You can see here, complete collapse. And in the picture below, it was the same case, some cuts until completely the cylinder is actually transformed in a plane and inducing this heavy pressure load. Similar problems when we have air within very thin membranes like bubbles that eventually will collapse. And this is an effort to model bubble motion and collapse of very thin membranes like here. Okay. Then we thought, why not use the information from the water forces to model erosion in the surface, like is the case in riverbeds. So in this case, what we do is we compute the tangential forces induced by the water in the vicinity of the bottom, and using these tangential forces, we compute the frictional work, and then when this frictional work exceeds a certain amount, then what we do is we release this mass. We basically model the erosion of a bulk area, and this area is transformed from being solid to being a fluid, and this is transported. So this you can see more graphically here. As friction work acts, the dam is eroded and the mass is transported downwards, and we can actually collect this mass later on, like another case where we see a dam which is completely wiped out by this phenomenon. And in the next picture we can see an example of how particles are being eroded, and then they are transported and they fall down. If you look in detail, they fall down later on and accumulate downwards. So this is a very powerful method to model erosion and transport and deposition of particles in water. And this is of interest, for instance, to model this phenomenon of the bridge pier erosion. In this case, we model the water flowing in the vicinity of the foundation. We model the water flow, then we model how particles are being eroded and then transported. This is what is shown here. And eventually the foundations of the bridge will come out, and this will induce eventual failure of the structure. Now, if we go to again to the sea areas where we have big waves induced, for instance, by tsunamis, people enjoy looking to the waves, but eventually they have to run. And we have performed extensive testings to to evaluate the forces of these waves on objects, and this we have applied to a number of problems in harbor engineering. This was the analysis of some new designs for breakwaters, which are of concrete cylinders, 5 meters diameter. But the most, I would say, challenging project in this field was the analysis of the stability of the construction of a long breakwater in La Coruña, in Langosteira Harbor. And this is work which is undergoing still for the next 2 years. Due to the heavy weather conditions, we have to analyze different scenarios during the construction of both the built part and the over the water and the underwater, the submerged part. And we have to model the slopes with the blocks. These are 150 tons blocks that are subject to very heavy loads induced by the waves. You can see here how the mesh is modeled. But in this case, sometimes the interest is not in the slope, which is quite stable, but in some objects like this 40 tons lorry that it's absolutely wiped out by the waves. And we have seen this picture before, and this is part of the study of the stability of what is called superstructure, that means buildings and cars adjacent to the harbor. In this case, we're focusing in the underwater construction. This is the test of how sand hill is being eroded by the effect of water. These are the preliminary works that are needed to build up a breakwater, and sometimes they are unfinished and they are left during a number of months. So we need to model how these hills will behave underwater. So this is stability of underwater constructions, which are also carried out with the same technology. But the emphasis in this case was the model and the analysis of this what is called closure area, which is when they stop working in winter, they build up this kind of closure, and then we have to analyze it. And we go from the analysis of the whole structure to the analysis of individual rocks. This is 1 ton block, and we compute which is the critical speed to which the rock will move, which is in this case 2 meters per second. And then we apply this critical speed to analyze if the rocks in the slope will move. So in this picture we combine the effect of erosion of this free shoulder. You can see how this is eroded with the motion, or the eventual motion of the rocks in the slope using this critical speed approach. This is a simplification of the full 3D analysis, which has been shown to give very good results. So these are typical measure points, and we compute these critical speeds in these so-called sensors, and then we can evaluate if a rock, for instance in this case, you can see here, if we compute the velocities, assume that the rocks are fixed, and then we let a rock free, and if the speed exceeds the critical velocity, this will move. Let me show you a very interesting case. This was Barcelona Harbor. This was 2007, and this is the fair of a big dike that is going to be recovered. This is what's called land reclamation. All these dikes are formed by building these big swimming pools, and then they are filled with dredgings, and water is left out, dredging sediments, and then we gain the land. For instance, in this case, in the left hand, we see this land which was gained, but there was a failure of the right hand side dike, and these caissons, they are big caissons which are 20 meters times 20 meters high and 40 meters length, weighing 36,000 tons, were shifted almost 100 meters. You can see here how it looks. And this occurred because there was a failure of this mountain here, this little hill that we used to monitor the work. There was a little failure due to some slip of the slope, inducing shaking of the whole domain, and the consequence was liquefaction. The sediment was turned into quicksand, and there was a small motion inducing a small acceleration time, a huge mass, and the whole wall collapsed. You can see Barcelona. My office is here in the middle of the picture, close to the mountain. And here we can see a reproduction of this phenomenon with this method. You see how this is the simulation. And you can see here that I'm going to show you how these models the falling of the hill automatically inducing this liquefaction. That means the sediment viscosity drops, it liquefies, and induces forces which shift these blocks away. This is another case here. You see how they move almost in a few seconds. They move, and this is a three-dimensional picture showing this phenomenon. And you can see here that altogether this lasted less than 1 minute, of course, less 40 seconds, 50 seconds, and this shows where these blocks went, which is these white points, and the curve shows our simulation. And you can see that we model globally the effect, of course not precisely because we didn't have enough information on the friction on the bottom, and also because water comes in immediately and stops the process in some areas, so that globally this was a very, very good result. Many applications that I'm not showing on hydraulics, on spillways, in dam engineering that can be analyzed with this technology. But I will move forward to the last part of this talk and shows you some applications of in a new area, which is nothing to do with water, which is how to model excavation with this technology. And this is of importance to design cutting tools for tunnel boring machine or for rock cutting tools for civil and mining engineering, including also explosions, but I will not talk today about explosions. And you can see that this is the PFEM applied to model the interaction between a tool and a soft soil, or even a harder rock. And precisely we are applying this technology that we apply for eroding the riverbed to erode, basically to wear out this block. We compute the frictional forces using the information from this boundary of elements until this frictional work exceeds a certain amount, and then we can model where, in this case, the mass loss in the rock, and also the wear of the tools. And we have applied this to individual discs and also to collection of these forming tunnel boring machines. So this is the simulation, how this penetrates the ground, and this is the glass view of the tunnel boring machine coming. And not only we model as I said, the penetration rate, but also how the different discs are worn out by the effect of the excavation. Other problems, in this case, this cutting disc, and we can see that also we can model the effect of mass loss. This is an acceleration mass loss. This is an academic example in the disc due to the penetration. And many practical cases of test problems presented to us by the manufacturers of the disc, companies like Hernek and Sandvik in Europe. They are using this technology to model the effect of, to model the quality of the cutting tools in different soils and rocks. this is examples of the wear of the surface, and this is used to measure the quality of the material, etc. Fire, as one of the last problems. Well, fire is very important, I don't need to insist, and it's a complex problem. It's analyzed from the fluid mechanics point of view, but here what we are doing is we are looking how objects will burn, how objects will melt, spread, flow, eventually collapse as well due to fire. And we have to include many different aspects. I don't have time to go into all of them, and the interest is basically to understand how objects, by burning or not burning, will contribute to a global fire, and eventually how structures will be safer, or how we can design objects which are less sensitive to burning and structures which are less damaged by fire effects. For that, we have performed tests together with our colleagues in the National Institute of Science and Technology in the US. Dr. Kathy Butler, for instance, provided us with this information, this experiment. Her and her team analyzed how a polymer melts and flows in an underlying pan, and the temperature of the polymer induce the change in viscosity, the temperature in the surface. So initially we have a high temperature, and eventually as it is heated, then the viscosity flows, inducing the flow of the heated area. So we're going to transfer the mass from the sample to the pan, to the catch surface. And this is what is shown here in this transparent. If I may show it to you, that this is heated, and what you are seeing is how the heated surface flows and falls down in the pan, and basically the whole polymer at the end falls down. And this is a detail. Again, here the nodes are marked with circles, and this gives a very, very physical representation of the melting and flowing of a polymer. And we measure the amount of mass which is collected in the catch pan, and we see that this agrees with the total mass because there is not gasification effects that they can be included. And in fact, we can include gasification, and as we include this effect, we compare better with the results in black, and our results in circle with gasifications match the experiments very precisely in this case. This is another object, this is triangular objects, and this is here heat source that you can see is melting the surface, and physically this looks like actually individual particles falling. Don't forget, this is a continuum representation, and if we wait long enough, all the mass will be transferred to the catch pan. Another case here. In this case, for instance, we have a triangular domain. This is heated, and you can see how particles are flowing. This looks like actually really particles, individual particles flowing over the surface of the sample one by one. This takes longer, but eventually, all the mass will be transferred to the catch pan. This is a 3D prism, polymeric, which is heated from this side. It's been melted and is falling. This is one of the first 3D cases that we did. This is a chair. It's been burned, falls down. And this is a case that shows how this can model complex shapes. But in fact, it was only the beginning. Now what we are doing is doing, of course, academic cases like this burning candle, in which we apply a heat source at the top, and this is falling, and falling. The wax is falling, and or how these three cables are completely detached from the protecting layer, polymeric layer, because it's burned. And now we introduce the burning of CO2, we introduce combustion effects, and I don't have time to explain that we model how air particles will approach the surface, how they will transfer heat, how they will be lifted by the convection, and eventually they will be transformed in CO2. So we have this change of phase from air to CO2 and motion of both air and CO2. I will skip this all the details of the problem. And we have many applications of this technology to model, for instance, how this was how a candle burns. For instance, when it's subject to when it's lit from the top, and this lasts forever. This is also what is shown here, even though this is in a closed domain, so eventually this will CO2 will cover the whole domain and will extinguish the candle. But it's very different when this is the CO2, for instance. You can see the CO2 distribution, which goes on until basically extinguishes the fire, because if we open now a window, the fire will continue. However, if we start from the bottom, like in this case, then immediately the fire is extinguished due to the convection, you see? And this is what we see here, that as we burn it, fire extinguishes a few seconds, not a few milliseconds, due to the convection. This is what is shown here. We start the fire and immediately it's extinguished. Now, what is being presented here is a chair, you cannot see it very well, that is being set to fire, and this is a cut of a chair. This is the back seat. This is the chair here, and there is a window at the top, so all the CO2 particles leave. So this will burn until the whole chair actually is, the polymer, you see, falls down, and you see the chair is completely turned into polymeric. This is a case more interesting. You can see here how this object is burns and falls down. And the final case, perhaps, is even clearer. There is a chair here. You see it. It's been set to fire into ends, and as it is burned, the shape changes, and the objects that fall down still have fire, and in a few seconds the whole chair is transformed into a mass, into a burning mass. So this is a very promising result that now we are validating with experiments carried out by different centers in Spain. So this is the conclusion. We can solve a variety of problems with this technology. The number of problems that we can solve grows and grows every day. Volcanoes are in fashion. We have seen recently the effect of these eruptions in the air traffic, and we have been involved recently in the modeling of the effect of these eruptions, modeling the magmatic chambers. This is the case here, and also experiment how to model the ashes, the flow of ashes in a domain. And this is a test that was carried out in Bristol, and that we reproduce here at different speeds. These are the ashes when the flow is slow, relatively slow. Still is a Lagrangian formulation. You can see how the particles are even, and for a more realistic speed, we reproduce the experiments better, as is shown here. This is a case where we have two liquids of different density. This is an old example, but it still shows very precisely the ability of the method to mix fluids with different properties, and this has a tremendous number of applications. And this is a line that now we are pursuing for different applications in mechanical, in chemical, and also in civil engineering. These are cornflakes in a glass of milk, for instance, in the wrong way. First, you should never put the cornflakes after the milk. It's the other way around. So, anyhow, this was just a test case. And particles in fluids. This is perhaps a line that opens a field of research for this technology. In the mechanical engineering, because many people are using this approach now to model tribology problems, frictional contact and wear between bodies, and this is a refinement of this technology to model the interactions. You see the layer, the interacting layer is very thin, and we model, you see here, the wear of the underlying surface. And we can also reproduce how the granular particles, for instance, in the compaction of metal powders, will be distributed in a die, and then will be pressed to conform metallic objects. Anyhow, this is some other applications of the method to cutting, to tribology, to what we call machining problems. And these are very academic examples that show the potential of the approach. So with this, I would like to finish. This is not the death of the finite element method. No, this opens, or this is the marriage of the finite element method with the particle world, and perhaps we find new areas exploiting this technology, not so much related to engineering, like this picture shows. And our students sometimes are more interested in other drinks than water. But anyhow, I think that has been a pleasure to share with you these minutes, and we will keep you updated of how this method evolves, and to put some faces to the names from left to right. I have Dr. Monica Demir, who did recently her PhD in CIMNE on multi-fluids and mixtures of fluids using PFEM. This is myself here, Dr. Julio Marti, who is doing all the work on modeling fire, Professor Sergio Idelson, they stand there, and Dr. Jose Maria Carbonell, he's done all the work in excavation problems. Miguel Angel Feliqueta is doing his PhD on fluid structure interaction in civil engineering. Antonia Larese, finishing her PhD on applications of PFEM to failure of earth dams. Dr. Kathy Butler from NIST provided all the experimental results for the fire test. Dr. Ricardo Rossi, who has done most of the work in fluid structure interaction and also fire modeling, supporting, and Dr. Pavel Rykov from Russia. He has developed many of the algorithms that have been used in these presentations. We are eating here calçots, which are special long onions, in Barcelona just a few months ago. So this is the end, el fin in Spanish. And if you want to find more about PFEM, please visit our webpage. There is a webpage which has been built for this purpose, and you can download many articles, papers, and videos related to this method. So, thank you very much for your attention, and until the next time.